Today we're going to talk about some of the new oxidation reactions that we brought up in class yesterday. I'm going to start by talking about ozonolysis, and then we'll talk about the Baeyer-Villiger oxidation. For the ozonolysis reaction, as mentioned in class, it reacts with alkenes and alkynes to cleave the alkene or alkyne pi bonds and leave behind carbonyls. It does react with alkynes, but primarily we're going to worry about reactions of ozone with alkenes. All right, so we're going to do ozonolysis, cleavage of alkenes, and synthesis of carbonyls. So let me give you an example, and then we can talk about some of the details. So if we have an alkene that looks like this, there are two sets of ozonolysis conditions that we can use for doing this cleavage reaction. We can use ozone and hydrogen peroxide. These are known as oxidative conditions. And in this reaction, we'll end up with a carboxylic acid plus a ketone. If we do the other conditions, in which the second step is changed, and we use zinc and water, or dimethyl sulfide, and I said that you'll see in Klein DMS, which is the abbreviation for dimethyl sulfide. These are reducing conditions, and under these conditions, instead of the carboxylic acid, we end up with an aldehyde. And we also get the same ketone product. So again, in both cases, we are cleaving the alkene pi bond. Under oxidative conditions, we get a carboxylic acid, where that H is. Under reducing conditions, that H stays the same, and we end up with an aldehyde. All right, so just to summarize, oxidative conditions, that's when we use hydrogen peroxide. We will synthesize ketones and carboxylic acids. We don't make aldehydes. Right? And then under reductive conditions, that's zinc and water or dimethyl sulfide. We synthesize ketones and aldehydes. We don't make carboxylic acids. Okay. The mechanism for this reaction is funky. All right, it's a cycloaddition reaction. We haven't talked about cycloaddition reactions yet. Right, so this is based on cycloaddition reactions. Cycloaddition reactions are in chapter 17. So we haven't talked about these type of reactions yet. We will, and when we get to that chapter, we'll talk about this in more detail. But I do want to tell you a little bit about it now so that it's not a complete mystery. Right? So this is based on a 1,3 dipolar cycloaddition. And again, we'll talk more about the details for this reaction in the future. But when you think about what's happening in the reaction that we have above, right, we have the alkene. And we talked about in class, I asked you to think about what the Lewis structure is for ozone. And if you've done that out, you know that the Lewis structure looks like this, where we have the three oxygens bonded together, one that's negatively charged, one that's positively charged, right? And we can fill in the lone pairs. And what happens in the dipolar cycloaddition is that we're going to make bonds to the alkene from the two end oxygens. So we can attack the alkene with a negatively charged oxygen, the alkene attacks the oxygen on the other end, and then the electrons flow on to the positively charged oxygen so that we generate a new 5-membered ring. And that's the key thing to know about dipolar cycloadditions. They always generate 5-membered rings. All right, so that's what we end up getting. This thing is called a mal-ozonide. Mal meaning bad. It's an explosive molecule. It makes doing this reaction a little bit dangerous / interesting. There are 2 more steps that occur that we're not going to worry about right now. All right, so this is where the cleavage occurs. So there's going to be something that promotes the cleavage, and then there's recombination. And again, when we get to cycloaddition reactions, we'll talk about this because it might actually mean a little something. But what we end up with then is a different 5-membered ring compound in which the cleavage has occurred, right? And that is called the ozonide. Right? And you can see that we've already cleaved the carbon-carbon bond at this point. Here is where we do the workup, and that would be either adding hydrogen peroxide or the zinc or dimethyl sulfide, right? And then we get the products. Okay? So those are the details for doing an ozonolysis reaction. And the final thing I want to do is just talk about one other case and show you some examples. And then we'll move on to the Baeyer-Villiger oxidation. All right, so the final thing I want to talk about with respect to ozonolysis is the reaction of terminal alkenes. Right, so this would be a good example to look at. So again, when we have an alkene that has 2 CH bonds on it, right, what happens when we do it under reducing conditions or under oxidizing conditions? And again, as with all ozonolysis reactions, we're going to cleave that bond. Again, we said ozone is like molecular scissors, and so if we do that in either case, we're going to end up with that ketone, right? The key question is what happens to the other side. And in the reducing case, there's really nothing surprising going on. We end up with formaldehyde, right? And for any terminal alkene under reducing conditions, we'll end up with formaldehyde. When we do the reaction under oxidizing conditions, right, we end up with carbon dioxide. Okay, so this is just a nice example of what happens, and we'll see examples of this as we move along. All right, so let's talk about the Baeyer-Villiger oxidation. The Baeyer-Villiger oxidation, we're going to oxidize aldehydes, so it's oxidation of aldehydes to carboxylic acids, and we're going to oxidize ketones to esters. Right? Aldehydes, carboxylic acid, and ketones to esters. Right? It's only a reaction of ketones and aldehydes. Okay? And what we will use for doing these reactions is we will use a per acid. Right? And as we talked about in class, again, this is just a carboxylic acid with an extra oxygen. Right? And our prime example of a per acid is MCPBA. Metachloroperoxybenzoic acid, which we've used for epoxidation of alkenes. It also does the Baeyer-Villiger oxidation. All right, so let's just take a look at a couple of reactions. So if we have an aldehyde and we treat an aldehyde with MCPBA, the Baeyer-Villiger oxidation will yield a carboxylic acid. Right? And this, as you'll note, is the same result we get from doing a chromic acid oxidation, except that here the mechanism is going to be different, but it's the same result. Okay? so same result as if we had reacted it with chromic acid. If we have a ketone, like acetone, with MCPBA, this is where we're going to yield an ester. Okay, so a very nice reaction in which we take a ketone to an ester like we saw in class yesterday. One interesting question is what happens in a case like this, where we have an unsymmetrical ketone. Right? When we do this reaction with an unsymmetrical ketone, experimentally, chemists have shown that the more substituted side is the side that becomes the ester. Right? So more substituted side becomes the ester. And it's a little bit complicated why that side becomes the ester. It has to do with developing charges in the transition state. The key for us to think about, though, is that when we have a ketone, the more substituted side is the side that's going to become the ester. That's the thing for us to remember. All right, so what I want to do is go through a mechanism and then do one example, and then we'll be done with this. So the mechanism of the Baeyer-Villiger oxidation, let's do the reaction with acetone. Reacting with a per-acid. The per-acid is going to attack the carbonyl in a standard carbonyl reaction. We're going to get a tetrahedral intermediate. As you would expect, the next step's a proton transfer. And this is where we get the key reaction in the mechanism. We're going to have a 1,2 shift, so that when we reform the carbonyl, we could obviously go backwards and break the carbon-oxygen bond, right? But another thing that we could do is to break a carbon-carbon bond and form that new bond, which is the result of a 1,2 shift. We have an atom moving to form a new bond with a different atom by a rearrangement. So if we form that bond, we then have to break the oxygen-oxygen bond, which is a very weak bond, and that's the driving force of this reaction, is breaking that oxygen-oxygen bond. Right? So that we now end up with a new carbonyl, positively charged, and now we have a bond to make the ester that we just formed. And we end up with the per-acid turning into a carboxylate anion, which we can then use to deprotonate the ester and generate our final product, so that we end up with the per-acid turning into a carboxylic acid and the ester product. Right? And one thing that I do want you to note is this 1,2 shift. Right? That might look a little bit exotic. And so what I want you to do is to think about other reactions in which we've seen something like this, where we've had an atom moving and doing some sort of rearrangement. And I want you to think about how you can relate this 1,2 shift to other reactions that are similar. And one thing I do want you to think about is how this is related to the oxidation step in hydroboration oxidation, that alkene reaction, in which we haven't talked too much about the mechanism, but I want you to think about this in relation to that reaction. So take a look at that in Klein and see if you think there are some similarities here. So the final thing that I want to do is just one example to make sure it's clear what's going on in these reactions. Right? So if we react this ketone with MCPBA, what product are we going to get? Right? And so we should be able to think about the mechanism of this reaction. So we're going to end up at an intermediate that looks like this after the per-acid adds to the ketone and we do a proton transfer. And again, we said that the more substituted carbon is going to make the ester. All right, so the more substituted position is over here. So that's the position that's going to migrate. So we're going to reform the carbonyl. The new bond we're going to make is going to be that bond. I did that wrong. Sorry. Is going to be that bond. So we can have this carbon-carbon bond migrate to form the new carbon-oxygen bond, and then break the oxygen-oxygen bond. Right? And then after we finish up the mechanism, we'll end up with formation of that ester. And again, let's just remember the more substituted side becomes the ester. And as we saw in class yesterday, this is a really nice reaction to do a ring expansion. All right, so this is a ring expansion reaction in which we've taken a 5-membered ring to a 6-membered ring. All right, and again, on the daily problems for Wednesday, you'll have the opportunity to practice both of these new oxidation reactions.